So in this video, we're just going to continue with our Schrodinger equation in spherical coordinates. So just to remind you, we were in Schrodinger's equation in 3 dimensions. This is the time-independent equation. We did assume we're in a central potential, which means U is just a function of R, similar to gravity or the electric force. And just to remind you, big psi was this time-independent psi times e to the minus IE over h bar t. And so what we did, I think 2 videos ago, we took our psi and we broke it up into, split it up into the radial part, the zenith part, and the azimuthal part. So just to remind you, for spherical coordinates, this point out here is x, y, z in rectangular coordinates. In spherical coordinates, it's r, theta, and phi, where these were the relationships between x, y, and z, and r, theta, and phi. And the volume element, little teeny volume element out here, is given by this. So anytime we do any integration over r's, we have to throw in an r squared. Anytime we're integrating over a theta, we've got to throw in an extra sine theta. Okay, this Laplacian right here, remember, was a huge term in spherical coordinates. And when we plug that in and put this in, we could turn in all the partial derivatives into total derivatives. Okay, and then what we did was we tried to put the phi's all by itself on one side. And so that's where I'm beginning here. We put all the phi's on one side, and all the rest of this, the r's and the thetas and the energies and the potential, everything else is on the other side. But since this is just a function of phi, and there's no phi's over here, and this is just r and theta, and since this has to equal that for all phi's and all thetas and all r's, the only way that can be true is if these two are equal to a constant, and we called it minus m sub l squared. Remember, it's not mass, it's really it's just m sub l quantity squared, which means that we set this equal to m minus m sub l squared, which we did, and we solved it, and we ended up, after we normalized it, we ended up with this for our phi sub phi, where m sub l could be 0, plus or minus 1, plus or minus 2, and so on. And we called that the magnetic quantum number. It's also, you could think of as the azimuthal quantum number. Phi, remember, is going around this way. Okay, and then we said the last lecture we said what was m sub l? Well, when we looked at total angular momentum, remember that's the definition of total angular momentum, we showed that the z component of the orbital angular momentum, so this is the orbital angular momentum of, say, the electron, if this is an atom, is given by this, minus IH bar partial with respect to phi. It only depended on phi. So if we, now that's my operator, if we operate on our psi, and we get lambda psi, there's our eigenfunction, eigenvalue. If we plug in our operator, IH bar partial with respect to phi, of psi, which is r theta phi, equals lambda r theta phi. Well, we notice right here that the r's and thetas just come right out in front of the derivative, and they just cancel, so they just pass on through. And so really the only thing I have to take the derivative of is phi right here. And when we take the derivative of this, it brought down an extra IML. But when you multiplied it by this, the I times the minus I gave me 1, and so we just ended up with that lambda being m sub l h bar. So now that tells, remember, those are the eigenvalues which you'd read. So the z component of the orbital angular momentum is equal to m sub l h bar, where m is given by this. Now remember, this is for any potential as long as it only depends on r, right here. We didn't say it had to be hydrogen or anything like that. Okay, so that's where we ended up last time. And so now what we have to do is we have to say, okay, now this, we have to solve this and set that equal to minus m sub l squared. And we're going to have to start with that because we need to find the big theta in the big R. Okay. So what I'm going to do is I'm going to take this equation and divide it by sine squared. So I'm going to actually divide it by minus sine squared. So this term will just be this without the minus sine squared on it. So I'll have 1 over R sub R d dr of R squared dr sub dr. So that's this first term. Remember, we're dividing by minus sine squared. If we divide this by minus sine squared, this becomes a plus, and we have an extra sign in the bottom. So we got plus 1 over big theta sine theta d theta of sine theta d big theta d theta. Okay, that takes care of this term. Now we're dividing again by minus sine squared. So this sine squared is going out, and that's a plus. So it's plus 2mr squared over h bar squared plus 2mr squared over h bar squared e minus u sub r and that equals the other side, minus m sub l, well, we're dividing by minus sine squared, so it'd be a plus m sub l squared over sine squared. M sub l squared all over sine squared theta. We're dividing by sine squared. Yes. Okay, that's all I did to that right there. Okay, now what I'm going to do is I'm going to put this term right here on the other side. Okay, so if I just put that term on the other side, this side still is going to be 1 over R sub R d dr of R squared d big R dr. And then we have that last term plus 2mr squared all over h bar squared e minus u sub r. And that equals, this term is going to be negative because I'm taking it to the other side, so it's minus 1 over big theta sine theta d theta sine theta, sine theta d theta d theta. So it takes care of this term when I brought it over there. And then I also have that term plus m sub l squared over sine squared theta. Okay, again, looking at this, we can see that this is just a function of r. That's all it is. And this is only a function of theta. Different function of theta, I guess I would say f, g of theta. Well, if this has got to be true for all r's and thetas, I could keep theta the same and vary r, but this equation still has to hold. That means that each one of these has to be a constant. So this is a constant and that's a constant. I'll just set it equal to, say, c. So now I've broken it up into 2 smaller pieces. This is equal to c, and that is equal to c. Okay, and well, let's throw everything on that side right here. If I throw everything on that side, this term becomes a positive if I throw it over there. So we got 1 all over big theta sine theta d theta sine theta d big theta, d theta. Okay, and then I'm going to move this term over to that side. Well, we'll put it at the end. And so then we also get plus c will be a positive, minus the m sub l squared all over sine squared theta equals 0. And then I'm going to do one last thing. I'm going to multiply everything by big theta. So it goes away from here, and it'll come into these two terms right there. So we end up with 1 all over the sine theta, d theta, sine theta, d big theta, d theta, plus c minus m sub l squared all over sine squared theta times big theta, and that equals 0. Okay, so that's the differential equation we have to solve right here. Now, this is a special differential equation right here. It actually has a special name to it, this exact differential equation. It's called the associated associate Legendre differential equation. Yeah, he spent a lot of time working this all out right here. And when you look at this differential equation, the only time you ever get, say, non-zero real solutions that give you trig functions that are between -1 and 1 is if c is equal to, only for special cases for c, well, you can get a solution out of here. C has to be L times L plus 1, where L can be 0, 1, 2, ... This looks like another quantum number. We could call it the orbital quantum number. Orbital quantum number. So this is going to be for the theta direction. So remember, before m was going around like this. That was the phi. The L is for coming down this way, right here. Okay, and one other condition here, and that is m sub l, we already said can be 0, plus minus 1, plus minus 2, ... But there's a limit now. It can only go up to plus and minus L. It cannot go higher than that right here. I imagine that this term right here would start going and changing the sign of it, and it wouldn't work right there. So the only time you get a solution is if these two have to hold right here. So that tells me that if L is 0, well, then m sub l can only be 0, because it goes from 0 all the way up to plus or minus 0. So m sub l can only be 0. If L is equal to 1, then m sub l can be 0 or plus or minus 1. Or it can be m sub l can be minus 1, 0, or 1. If L is equal to 2, m sub l can be minus 2, minus 1, 0, 1, 2. L equals 3, and so on. It's going to be minus 3, minus 2, minus 1. So m sub l equals minus 3, minus 2, minus 1, 0, 1, 2, 3. It looks like you get, depending on what L is, it looks like you get 2L plus 1 total amount of m's out of here. Okay, and so So this tells you the differential equation and what C can be and what M sub L can be, but what are the solutions for theta? Theta. The solutions. Well, the solutions are a bunch of polynomials. Remember what polynomials are, right? You know, x squared minus 2, x cubed minus whatever, x to the fourth, x cubed, x squared. Those are all polynomials right there. It's just a group, a whole bunch of polynomials, higher and higher order. Except in place of x, in place of x, you put a cosine theta. That's the only difference. And they give them, instead of calling it big theta, they call it p. They call it this p, and it depends on two quantum numbers. It depends on L and M sub L. So they'll write it like this. And in place of the polynomial x, you put a cosine theta. So those are the solutions. And just to give you an idea on what some of these are, for this first one right here, this, well, I can't put all those in here, but let's just say for L equals 0 and M sub L equals 0, now we've got a P00 of cosine theta, and that's just 1. Okay, so the first one is just 1. The next one, say L and let's go 1, 0. So let's just say L is equal to 1, M sub L equals 0. That means we would have P sub 1, 0 of cosine theta. And that's just cosine theta. So it was probably an x if before you switched all your x's to cosine thetas. If L is equal to 1, M sub L equal 1, then this is just P 1, 1 of cosine theta, and that's equal to minus sine theta. So this must have been something like a 1 minus x squared, or an x squared minus 1, square root right here, so to give you a sign. Okay, and then they'll be getting larger and larger. Let me look at, now you can go onto Wikipedia and look up under Legendre polynomials. So these are called Legendre polynomials. Now they might put them in terms of x's, but if they might also give you a list where they replace all the x with the cosine theta, and that's what you should be getting. Let me go up. If I were to go a little bit higher, how about L equals 2, M sub L equals 0? Well, then this P sub 2, 0 of cos theta is equal to 1/2 3 cos squared theta minus 1. 3 cos. Okay, and then as you keep going down, these terms are going to get bigger and bigger. What they're going to give you is they're going to give you wiggles in this direction, in the theta direction. Remember, this gave you wiggles along this direction. Remember, you can write this as a cosine and a sine. So you got wiggles this way, and now we're going to get wiggles along this other direction too. Now, these guys are all orthogonal to each other. That is, if I were to integrate this times this, I would get 0 when they're not equal, right here. Now, they're not normalized, so I'd have to put a normalization constant in to make them normalized, but they were still, they're still orthogonal. That is, if I were to integrate this for two different ones, say P sub L1, M sub L1 of cosine theta, star P sub L2 m sub L2 cosine theta. Remember, when you're integrating, we're integrating theta. So remember, when you're integrating theta, you got to put the sine theta with the d theta. Sine theta, d theta. And we're integrating from 0 to just pi. Remember, the phi goes all the way around, so I don't have to worry about the other side. The theta only goes down to pi. Okay, so what this thing will be is, this will be 0 if these guys aren't the same and if these guys aren't the same, right here. Okay. Now, it's much easier to instead, you know, this was like our theta function. This is like our big theta, sub theta. But if we were to combine the theta with the phi, that would cover all the wiggles in the theta and the phi direction. So we're going to define a new variable, big Y, and that's going to be just the two put together, the theta sub theta and the phi sub phi, right there. And they have given these a name to them, these Y's, which they use a lot more than the thetas and the phis. These Y's are called spherical harmonics. Now these are wiggles on the surface of a sphere. Surface of a sphere. So if we were to write it out with all the terms over here, we could say Y, and it's going to be dependent on two quantum numbers, L and m sub L, and it's a function of theta and phi, and it has the theta part, so it has this part in it, P sub L, m sub L of cosine theta. It also has our phi in there, which is this, e to the I m sub L phi. I'll throw all that other stuff out in front in just a minute. So it's got the e to the I m sub L phi. And then we have the normalization constant out in front. Well, it's got that 1 over the square root of 2 pi from the phi, but it's also got some other stuff from this. And it actually ends up being minus 1 to the m sub L times the square root of 2L plus 1 times L minus m sub L, L minus m sub L factorial, all over 4 pi times L plus m factorial. That normalizes it. So this is all normalized. So if I were to integrate this with itself, with the star, that is the integral, now we have to do a double integral because we're integrating over theta and phi. So our d phi goes from 0 to 2 pi, and our d theta, which happens to go with the sine theta. Remember, we always have to put a sine theta when we're integrating over that. That goes from 0 to pi. And then we have our y star y. Y, L, m sub L star of theta phi. Two different ones, L1, m sub L1. And we've got Y, L2, m sub L2. Sorry, ML2, right there. Since they're orthonormal, this thing right here gives you our Kronecker delta. L1, L2, and also m sub L1, m sub L2. Okay. So that just means that they're orthonormal right here. Now, what these are is, this is wiggles on a surface of a sphere. So if you had a sphere here and there's different values all over it on the surface, and you wanted to get an equation for What could that be? Say the magnetic field at every spot on the surface of the Earth, or the temperature at every location on the surface of the Earth. You could write that total function as the sum of a bunch of these y sub y, l, m sub l of theta and phi's. Oh, you'd need a constant out in front. L, it's going to depend on L and M sub L. You can write this up just like we did with the infinite well. Didn't we say we could write the infinite well as the sum of all the eigenfunctions right here? We can write this also. And remember, we could make, with our infinite well, we could make any pattern with a sum of all of our sine n pi x over l's. Well, I can make any pattern I want here with enough of these. So anytime you're trying to map out something on a sphere, you're probably going to be using something called spherical harmonics. It's not just used in quantum mechanics. It's anytime you have a value on a sphere. Now, if we were to look at these values, what these things are, well, for L, let's just make a list here. When L is 0 and M sub L is 0, so you can see over here, this would be minus 1 to the 0, which is just 1. And here you get 1. And here you got 0 minus 0, 0 factorial, which is 1. And here you got 0 plus 0 factorial is 1. So you just got 1 over the square root of 4 pi. And we said that first one was 1. And that's 0, that's 1. So everything is just 1 over the square root of 4 pi. So this y sub 0, 0 is just 1 over the square root of 4 pi. Okay, and now if we were to look at, say, 1, 0, again, anytime m sub l is 0, this is gone because you just get 1. When this was 1, we said it was a cosine, so we know there's at least a cosine in there. And then we had this number here out in front. If you plug in the l's and the m sub l's, it's just square root of 3 over 4 pi. So you get the square root of 3 over 4 pi cosine theta. Okay, and how about if we look at, say, 1 plus or minus 1 right here. If it's plus or minus 1, you'll notice this right here. When this is a plus 1, this becomes minus 1 because minus 1 to the 1 is minus 1. So this would become minus plus. And then we get the square root. That's going to end up being 3 over 8 pi. And then we're looking at the 1 plus or minus 1. They're both, I think this is sine theta right here. So I think it came out to be a sine theta e to the plus minus I phi, and so on. Let me look a little bit further down. How about 2, 0? Well, this one is just going to be the square root of 5 over 16 pi. 3 cosine squared theta minus 1. Let me do one more. 2. Instead of the plus or minus 1, let's do the plus or minus 2 right there. It's a square root of 15 over 32 pi sine squared theta e to the plus minus, since m is plus or minus 2, this would be plus or minus 2I phi. 2I phi, and so on. They just get bigger and bigger. Again, go on to Wikipedia under spherical harmonics, a whole table. This thing just goes on forever right here. Okay. Well, you might say, so that means if I wanted to calculate, since this is the wave function for the theta and phi part, the only part we haven't gotten is the radial part. If we were to square this, that is, if we were to go y sub L theta phi star m sub L y sub L m sub L theta phi. If we were to multiply these two together, we already know psi star psi is the probability of where you would find it on the surface of a sphere. So this is the probability of finding the particle, Now, only on the theta and phi direction, not the radial part out. We haven't worked out the radial part, but this is just the angular, what theta and phi would be. Probably finding at the theta and the phi part, right here. Now, if you look at a lot of chemistry books, a lot of them show the pictures of these right here, because they're the probability, like for an atom, where you're going to find the electron. Well, if we look at it for this one right here, now you're going to multiply it by its complex conjugate, but it's real. But so if you multiply that by its complex conjugate, it's just 1 over 4 pi. So if you were to plot it out for all thetas and phis, it's just a constant. It's 1 over 4 pi, and so it would just look like a sphere. It would just look like a sphere. Remember, what you're plotting is this way. When they plot it, they're plotting this as the probability, and since the probability was the same in all directions, it was 1 over 4 pi. Well, if you go out the same amount in all directions, it just ends up being a sphere. Okay, so if we now let's look at this one. This was the L equals 0, M sub L equals 0. Let's look at the L equals 0, M sub L, 1, 0, which would be this one right here. So here, if we were to plot this on this is a three-dimensional, this is right there at the center, you'll notice right here, cosine theta is maximum. Remember, theta is this angle right here. It's how far you are from the z direction. Cosine is a maximum when this is 0. So you're a maximum right there. Maybe I should do this in a different color. So you're going to be a maximum here. Now, as you work your way down this way, it gets smaller and smaller. The cosine function gets smaller. So that means you're coming in. And matter of fact, when you get all the way to 90 degrees, cosine of 90 degrees is 0. And so you don't have any. So what you're plotting out this way is the probability. Now, remember, you're squaring this, so it's really cosine squared. So when you go to the negative down here, there's no negative, you're still back positive. So it's going to go like this. Now, this is going to be true for all phi, because it doesn't depend on phi. And so what you're going to get, if you just swing this around, you get, I like to call it, the snowman. I don't know what they call it in the chemistry books. I call it the snowman right here. Now, you got to be a little careful about what they're plotting here, because it's, you think that's the way the electron is. No, this has nothing to do with that. What they're plotting is they're plotting out the probability as a function of theta. That doesn't, really the way we should look at it is, if you are, remember, we're looking at a surface of a sphere. So put a sphere out there. Because we haven't really done anything with the radial part. And wherever the probability is biggest, where was the probability biggest? Here and there. So we really should think of it as, it's most of it, it's all on the surface of a sphere, but it's all near the poles, That's what this thing is. Remember, we're looking at the surface of a sphere. And this thing says the poles are enhanced right there. So that's the way you should look at it, but a lot of times they'll show pictures of this, so just don't get these two mixed up. Now, if we look at this one right here, the 1 plus or minus 1, well, it's not going to make any difference whether we do plus or minus because we're squaring it, and that term's going to go. And even this goes, because when you multiply that by its complex conjugate, it's gone too. So really, you're just looking at the sine function. And you might say, what does the sine function look like? So if this is m sub l equals 1, m sub l equals either plus or minus 1, it doesn't matter. If we're looking at the sine function, the sine, when you're at 0 degrees, which is right there, sine of 0 is 0. So this thing would just be 0. Now, as you work your way down, sine increases until you're right there and it's at 1. So it's going to look something like that right there. And then when you go on further, when you go all the way to pi, it's going to come back to 0 again. And then you're going to get it going the other, remember, it's the same all the way around. So wrap that around this, and we could call it the donut. I call it the donut. It's just that it doesn't have much of a center to it right here. It's kind of closed in on itself. But that's not what we should think. Really, where we're talking about it, it's back to this picture again, but it's peaking near the poles. Near the equator. So this one would be peaking over in this part right here. Goes around like that. Okay, and since there are 2 of these and only 1 of these, that's probably why there was a factor of 2 in here. When you squared this, this is 3 over 4 pi, this is 3 over 8 pi. Since I have twice as many of these, I better make these half as much right here. So okay, and so that's what you get. So really, for the electron, you can think of the electron be more along this xy plane, and for the m sub l equals 0, it's more toward the poles right there. But most pictures are going to show donuts and snowmen right here. Now, as we keep going to larger and larger values here, we're just adding more wiggles this way, right here. We're just adding more wiggles. These wiggles never change because when you take this and multiply it by its complex conjugate, it always drops out. So you're just getting more and more wiggles this way, right here. You notice this had the least amount of wiggles right here. Well, I actually, if you go into Canvas, there's something called Spherical Harmonics Lab, and it's going to show you a lot of pictures. If we come around here, here is some of our pictures. This was that first one, the L equals 1, M sub L, L equals 0, M sub L equals 0. That was our sphere. Here is our donut and our snowman. There would be 2 donuts, but I'm only showing you the plus ones. Remember, there's a minus one over here. Okay, so this is the L equal 2 case. You got M sub L equal 2, 1, 0, and then minus 1, minus 2 right here. But we could call, so this one over here, it peaks at the poles and a little bit on the equator. This one really enhances it on the equator, and this one's like halfway in between. Here, this is the L equals 0, 1, 2, 3. So you got 3, 2, 1, 0, and then they'd be the same going back the other side right there. And we could even go down one further right here. So there is, for the L equal 4 cases. You can see there's just a lot more wiggles in here. And you'll notice that when I put these together, when I fill up the entire shell, that is when I include all of the L's, the L equals 1 for the M sub L equals 0, and the M sub L equals 1, plus or minus 1, when I combine them all together, it kind of fills in the sphere. And there's actually a theorem that's called Unseld's theorem that says, Unseld's theorem, well, it says if I were to sum up, if I were to take and sum all the m sub l's for a particular L from minus L to plus L, because that's what m sub L could be, and if I were to add up this y sub L, m sub L, theta phi squared right here, this would be equal to a constant. What does that mean? That means it becomes, remember, what do we get for a constant? We got the sphere. So when you pick one of these high cases right here, where you have, say, L equals 5 or L equals 6, well, one of them will be peaking over here. One of them will be peaking in this region, you know, and as you go around. Another one might be peaking, some other colors here. Another one might be peaking in this region, but when you fill them all up, you get a nice perfect sphere, which means you probably can't add any more electrons into there because you've got the full sphere covered right here. So that's what happened. We could think of this as a filled shell, maybe, but it's called Unseld's theorem. Theorem. Okay, well, we'll look. We still haven't figured out what does the L quantum number mean, because we figured out what the L quantum number meant. The L meant was tied to the z component of the orbital angular momentum. So on the next video, we'll figure out what the heck the L means. Okay.